In this video, we're going to show how the Tektronix MDO4000 mixed domain oscilloscope can be used to track down the source of a low duty cycle transient RF emission from this circuit board. The transient RF emission we're looking for lies between 100 and 200 megahertz. So we'll start by just turning the spectrum analyzer on alone, setting the center frequency to 150 megahertz and the span to 100 megahertz. And we'll adjust the reference level to -10 dBm. Near-field RF probes, such as this H-field probe, can be used to look for emissions on a circuit board by bringing the probe near the circuit board and scanning around looking for emissions. After scanning around for a few moments on the circuit board, we found our troublesome near-field emission right here. You can see that the magnitude of this signal is bouncing up and down by more than 10 dB, and this is the problem that has been reported. The spectrum analyzer is currently in free run, but can be set to acquire spectrums in response to a trigger. In addition to being able to trigger on any of the scope analog or digital channels, we could also trigger on RF power. We do this by entering the trigger menu, selecting the source to be RF power. We're going to set the mode of the trigger to normal, so we're only going to get acquisitions when the trigger is satisfied. With the slope set to rising, the broadband RF power detector will trigger the scope when the level exceeds, in this case, -30 dBm. If we adjust that level slowly down, we'll reach a point where our transient burst begins to trigger the scope. And now we can actually see activity again here because our bursted signal is exceeding that power level. To verify we're actually triggering on our transient signal, we'll momentarily switch back to free run. And I can see the magnitude of this signal varying by that same 10 dB again. And now when I'm triggered, I'm only seeing that signal at the higher level. Since the scope captures the RF signal over time, we can use our RF versus time traces to look at various aspects of the RF signal versus time. By turning on the RF amplitude versus time and adjusting the vertical scale, and let's adjust our horizontal scale to capture a bit more data over time, we can actually see these little RF bursts. These are bursts of RF power that are occurring periodically over time. Pause the scope momentarily and verify that these bursts are indeed our signal of interest by moving our spectrum time through the record. We can see our signal level here is about -38.9 dBm. If I had moved the spectrum time to in between the bursts, we can see that power level drop to -51.3 dBm. If I adjust it over to the next burst, we can see that signal again grow up to about -39 dBm. So now we know that our signal of interest is occurring at this rate. Simple cursors can be used to take a look at the duration of the RF burst, in this case, in the neighborhood of about 10 microseconds, or the repetition interval between the bursts, in this case about 94 microseconds. This information alone may be enough to tell you the source of the emission. If the time domain nature of the signal is not enough to help you identify it, we can use the fact that we're triggering on the signal itself to help us identify a coincident signal. With the scope still triggering on the RF signal, let's add channel 1 and start probing around on the board with our oscilloscope probe to look for signals that are coincident with that event. Signals that are unrelated to the repetition interval of that event will appear completely random and free running with respect to the signal. But a signal that is coincident with that event will actually show up and be synchronous with that RF emission. So in this case, we've found a signal on our board that is occurring exactly coincident with our RF bursts. Identifying an electrical signal that is coincident with our RF emission is the key element to help you track down the ultimate source of this emission.